Okay, what we're going to do is take a 3-day class and pound it down into 1.5. And to do that, I'm going to just throw out toss out a couple of chapters before we get started. So I'm going to do Chapter 1, Introductions, Chapter 2, and Chapter 4. I'm not going to worry about Chapter 3 because it's stuff you probably already know anyway. So anyway, you never know what you're testing. Now, the way this course usually progresses is, we're talking about the main objective is to figure out how to analyze and control our tests, in particular when we're controlling an electrodynamic shaker or hydraulic shaker. And the way it progresses is that we do shock first, because it turns out that shock is the easiest to reproduce with an electrodynamic shaker. And then we're going to do random, which is the next easiest to do, and then sine. And do you guys do sine testing at all?
Oh, yeah.
You do. Okay, so we're going to have to do
sine. Just single sine wave. So we go
sine sweeps. Okay, do you do sine sweeps too? Okay, so we're going to, I was hoping to toss that, but I guess we're not going to get to. Okay, now we're going to talk about assumptions that we've talked about already before some, but when we start talking about control systems, it is much more important that the systems be linear than it was for any of our other discussions. Yeah, sure. Okay, here's your questions for tonight. Oh, I need a copy too. So anyway, all of the things that we're going to talk about in this class assume that the structure that we're testing and our instrumentation is linear. And if it's not, then that's going to get us in some trouble. So the basic idea here, basic idea of linearity, is that if I put in a command, I get a response that looks like this. If I double the command, I get a response that's twice as big. And the other important thing is that for a linear system, if I put in a sine wave, I get a sine wave back out. So if I excite my system with a sine wave, and I don't get a sine wave back out, that is the first indication that my system is nonlinear. And so a lot of the really cool, simple rules that we're going to talk about don't hold anymore. And we'll see some examples of what happens. For instance, one of the models that I've got, which I hope I can get running, is that I have a closed-loop control system emulated in my computer. And when I use a linear transfer function, everything works cool. When I make it nonlinear, then everything goes goofy in short order. Okay, so here's some examples of linear systems. And one that we've already looked at in the last course is a one-pole filter or a two-pole oscillator. And these are elements that we used in the last course as parts of filters. And so here's the simplest low-pass filter, resistor and a capacitor. Its transfer function looks like this: gain of 1 at 0 frequency, at its critical frequency, which is 1 over 2 pi RC. It's down by 0.707, and it rolls off at 6 dB per octave. And again, this is something that you need to keep in the back of your mind when we're talking about multi-pole filters. For filters that don't bounce like the elliptical ones, what you get is 6 dB per octave per pole. So an 8-pole filter is going to roll off at 48 dB per octave.
So it's going to be 3 dB without 2.
I'm sorry?
Will always be 3 dB at the top.
It will always be down 3 dB. Yes, that is the definition of the cutoff frequency of the filter, is where it is down by 3 dB, with a couple of exceptions that I'm going to ignore those. So, okay, so anyway, that's the basic filter. And there's the definition of a 3 dB point, and that is where it is down by 1 over the square root of 2, 0.707. Why that was picked is beyond me, but that's the fact of the matter. So one of the problems here is that this is sometimes called the usable bandwidth of the system. So it's, if I have a system and they say that it's good from 0 to a kilohertz, that means that it is actually down by a factor of 30% within its bandwidth, if it's a one-pole filter definition. So let's take a closer look, just expanding what's going on up here, at what's going on. And if I've got a one-pole characteristic, which an awful lot of our instrumentation has, its nominal cutoff frequency is all way out here at 1. But if we're interested in specifying the accuracy of the response, we have to come back to about 1/10 of the natural of the cutoff frequency to get down to 0.5% error. And one of the things that some of the filter manufacturers specify is not the 3 dB cutoff point, but the 1% cutoff point. So the essence of this is that if we're interested in data to be accurate to 1%, the bandwidth is not all the way out here, it is actually just back to here, which is about 15% of the total bandwidth that's quoted by the vendors. Next thing up the food chain is the two-pole filter, which is a emulation of a vibrating beam. Two-pole oscillator. It represents this. You guys have all seen the spring mass damper dealie, right? I'm preaching to the choir on that. And the model that we're talking about here, that we're going to be talking about most of the time, is that we're driving the base with some sort of motion, and we're measuring the response that comes out of it. And when we do that, we wind up with a transfer function that's got a gain of 1 at low frequency and peaks up at its natural frequency, and then above the natural frequency it tails off. And it's a two-pole filter, so how fast does it roll off out here? 12 dB per octave, okay? 6 dB per octave per pole. And when you look at the response of this is viscously damped, which is the model that most of us are used to, where the damping is proportional to the velocity. Then the transfer function's got some fairly neat characteristics. If I measure the transfer function, I can calculate, knowing the minus 3 dB damping, or 3 dB bandwidth, I can calculate the damping coefficient. Or I can calculate the damping coefficient because it's 1 over 2 times the gain at the natural frequency. Those equations are right here.
Okay, I was going to say I didn't write those down.
Yeah, no, they're here. So, you know, the upshot of it is that I'm not going to worry about the equations. You can worry about them later. But the point here is that our structure is going to, our structural response is going to be very heavily dependent on the damping, this damper right here. And if the damping is low, then I'm going to get a lot of response at the resonant frequency. If the damping is high, I'm going to get a very mushy response. And one of the things that we talked about, and we'll talk about it again, but we've already talked about the damped accelerometers that Best and some of the rest of you guys are using, strain gauge accelerometers, and they are designed, they're mechanically look like this. They're a spring mass damper, And what they've done is arranged done plates of games so that the damping is high enough so that there's not much gain at the resonant frequency. You know, when we looked at the data this morning that we got from Mark Remmelman, it had those two great big bangs out at 300 kilohertz or whatever it is. That's an undamped accelerometer, and that's bad. Okay, and so the more modern stuff is doing a better job of knocking that stuff off. Okay, real structures, of course, are a whole bunch of these guys put together. And when we do that, we wind up with a whole bunch of modes superimposed on top of each other. And I've just added a few of them to give you an idea what the transfer function of a real structure looks like. But a real structure really doesn't look much like this anyway. Anyway, we have talked about spectra a whole lot the last 2.5 days, but what we haven't talked about is how we might plot the data, how we might plot our spectra. And by playing a variety of different games, we can make our data look very different. We can hide things we want to hide. We can amplify things we want to show off. And the question is how we should be plotting our spectrum. And the choices are linear or log on both of the axes. And which do you guys use?
Trick question. Depends on who I'm reporting to and what I'm doing.
Okay, all right. That's a good answer. And what I'm going to do is tell you what I think the trade-offs are. Okay? You got any favorite plot formats?
Depends on who's sitting there to make it shut up.
Okay. All right. So anyway, have any of you ever seen this plot format?
Yes.
Yes, you have. Why?
Why?
Okay.
Usually-
One of the things we're going to learn when we talk about the Fourier transform, it gives us real and imaginary components. And that's what we're plotting here. This is the real and imaginary components of a mode. And this is a plot format your packages have, but it's not particularly useful. It's just confusing. So we're not going to see much of that. What we are going to see, perhaps, is linear. And here our mode looks like this. You see it peaks up. We've got good definition of what's going on up here. Roll off like this. We don't see this very often, but I'm going to show you some examples where it would be a good idea. What we see most of the time is log. And here it's really obvious that the response, the gain, is 1 at low frequency. And the other important thing is that we see that in a log space, it is rolling off as a straight line at 12 dB per octave. So in some ways, this is a better format to show the physics than this is. Other possibilities look like, other combinations look like this. If we've got an input and an output, then we get a plot that looks like this. This is called a Bode plot. This is another guy who worked at the Bell Labs with Shannon and Tukey and all of those guys. And here we've got a log magnitude, and phase is plotted linear versus frequency. Now, one of the things that you see when you do a Bode plot is if there are two modes, the phase falls behind at the modal frequency. It's minus 90 degrees at the modal frequency. And then if we have a second mode that's going to roll the frequency some more, or roll the phase some more, which is actually coming down here. But what we're going to do is say that minus 180 degrees is the same as plus 180 degrees, and so we just do a hop and make our plot plus and minus 180 degrees. The truth goes down like this, what we're saying is that we're going to plot it like this instead. So if you see any hops in the plot, it's not a hop in the data, it's a plot, phase shift anomaly, whatever you want to call it. So what I've got here is a bunch of different examples. This particular one is a bunch of modes. And what it is each of these blobs is 2 modes. And when I plot it linear, it looks like there's only one mode here for one thing. But the other thing is that it's kind of screwed up the physics. Physically, modes are logarithmically spaced. And so when we're doing structural analysis, we usually want to use a logarithmic scale. Okay? And what this does is it makes these mode pairs look like they're pretty much the same, or the spacing is pretty much the same. So for structural analysis, very often we want to use log-log. Now, how about vertical? Here's linear vertical. Here's log vertical. Linear, log. What's the big difference that you see? What's going on right down in here? When I'm plotting linear, it's there, but it's tiny. Okay? I put it in log space, now I can see it. What have I increased? My dynamic range. Okay? Linear vertical plot, you can only really see stuff that's a few percent of full scale, or a few percent of the maximum. If I do a log plot, then I can see the little tiny stuff very easily. In return, linear, I can really easily tell the difference in magnitude of the things that are big. And in log, they don't look so big. Okay? It's all the same data, but we can change the look of it by the choice of plot format. Which one do you want to use? Okay, what are you looking for? Let's say we were doing strain gauge testing.
Okay.
What's wrong with strain? Well, I shouldn't say what's wrong. What is a bad feature of strain gauge testing?
I don't use strain gauges. So
Not either.
Well, the signal is small.
yeah, okay.
So the signal to noise ratio is going to be small.
Okay.
Okay. And also, you know, it's strain or stress that caused it, that breaks things. So do you care about stuff that's down that's less than 1% of the max? What you care about is the big stuff. Okay. So if I'm doing a test that doesn't have huge dynamic range, good dynamic range, and I do want to see the peaks in detail, then I want to use a linear vertical scale. Okay, if I've got a super duper gate acquisition system and instrumentation system that I want to show off the dynamic range of, then I want to use log. Okay, so if my signal to noise ratio sucks, what am I going to do? Linear, you bet. Okay, I'm hiding what I don't want you to see. Okay, perfectly legal things to do. Okay, let's say we're looking for something else. Let's go back to linear. Okay, this is a square wave. Okay, remember what the characteristic of the square wave was that we really liked?
Multiple frequencies.
Multiple frequencies, and if we plot it in log-log space, it's a straight line. Okay, so if I'm using a square wave as my testing tool for whatever, what I want to do is have an easily recognizable characteristic that I can use as my baseline of what's going on. Does anybody, do either of you see anything sort of strange about what's going on here?
Tails off at the end instead of being straight.
Yeah.
And it's also, I don't know if it's an issue with your binning, but the initial frequency is more than one bin wide. I don't know if it's display or not.
That's display.
Okay.
Well, actually, each line is a triangle.
Oh,
Okay, so at the low end it looks fat. But your point is well taken. The fact that it's a log horizontal scale means that it expands that down here. What's causing this? Okay, what's the rule that I said? If you've got suspicious looking data, what's the first suspect?
alias.
Aliasing. So it turns out I cannot do a perfect square wave without some aliasing. Okay? And when I plotted this in log space, it was very obvious that this was going on. If I do it in linear space, well, I can't even see it vertical. Okay? Doesn't show at all. So, in this particular case, I want to use log scaling. Okay. Do you guys do vibration tests? And you are given a spectrum to match. And it's probably straight lines. It's straight lines in what space?
Yes, we are expected to see.
But log or linear or what?
Usually log.
Always log.
Not always.
Oh, okay.
I have received it in linear log and went, what the heck?
Okay, well, if it's, you know, if the spec is straight lines in log space, it's not going to be straight lines in linear log space or linear space. Actually, the only thing that turns out straight in both is flat, obviously, or something that's at 45 degrees. As it turns out, if it's going up at 6 dB per octave, that winds up being a straight line in either one. But how often you see that? So, obviously the deal here is the usual thing is that your vibration PSD spec or your SRS spec that we'll talk about later is given to you in log space, and it's all straight lines. Why would anybody give you anything else?
The IVA spec for my interface cards, it's a international spec, comes in linear log.
And is it straight lines in linear log?
No.
Up across and then it slopes down.
Yeah, I had the same thing. It was a spec from Korea or something like that. And
A lot of the
linear
international
log.
specs are
That's linear horizontal? Or linear?
linear horizontal.
I remember.
So some of it's straight, some of it's curved?
It's linear horizontal, not vertical.
Oh, okay.
Yeah.
Yeah.
Okay,
I've seen something.
and this looks like what they gave you?
Yeah.
It's, okay, so obviously it was designed in log space, and then they gave it to you in linear log.
At least with the spec, they give you the graph, but then they also specify in words. They're actually good with
Isn't that interesting?
electronics. They do a lot of linear log.
You don't deal with a lot of international customers, like, huh?
I guess not. Yeah, maybe that's a good thing.
Trust me, it is, because when you have to start converting units from weird things back to normal things, it starts converting.
Let me tell you something that happened. The biggest, Congress has made some enormous mistakes.
Okay, that's a
You don't
Very
want to
general
start this
comment.
conversation.
All right, okay. But the worst one of all is that when I was going to school, the college, everything was done in metric. And the United States was going to convert to metric, I think, in 1970. And the American automobile vendors put all of their clout on Congress and con Congress into killing that change because of all the money it was going to save. Okay, well, needless to say, 40 years after the fact.
Find an American-made car without metric screws on it. It'll be
Yeah.
impressed.
Yeah, it's just a disaster, and it's inexcusable. Okay, so anyway, the whole point of having different lin-log combinations is to show off or squash whatever features you want to talk about. And oh, the other one is harmonic, and oh yeah, that's the square wave. And let me get that down back. Okay, if I've got a square wave, there you want to do that in perhaps two different ways. We just said you should do it log to get the characteristic of the magnitude, but you want to do linear log to show that all of these guys are equidistant apart. So if you're trying to show harmonics, then you want to use linear horizontal. Okay, all of these are examples of that. Have any of you seen a plot format that looks like this?
I have.
You have. Why?
I wish I knew.
Okay.
It's usually related. I've only seen it in some of the shock specs, where they start calling out real and imaginary, and then phase shift and magnitude. And it didn't make sense to me why they did it for shock.
Okay, it doesn't make any sense to me why they do it for shock
I'm
either.
glad I wasn't alone.
Okay, what this is usually used is in modal analysis. And as it turns out, if I have a viscously damped mode and I cross plot the real versus the imaginary, it traces out a perfect circle, which of course is warped. Oh, it looks like a perfect circle up there, but on my screen it's warped. So anyway, what's going on here? Frequency 0 is low response, and then as you go to higher and higher frequency, the phase shifts around, and then right here is maximum response, and then as I go to maximum response, which is at this frequency right here, and then as I continue on around, it gets lower and goes back to near 0. And when I say near 0, the fact that this is a linear plot, I can't tell the difference between 0 and 1. I've lost the resolution at low frequencies. So anyway, this is called a Nyquist plot or an Argand plot, it's used in modal analysis because well, one of the reasons is that if the structure is nonlinear, this won't be a circle. And if it's hardening, then the circle will be squashed, smaller, an ellipse. And if it's a softening spring, then it's going to be bigger in the vertical direction. So this is one of the ways that you might characterize nonlinearity, although that's a thankless task under any conditions for the state of the art that we've got right now. Okay.